Okay, folks, let's do this. All right. Okay, ready to go. So today the plan is to continue a little bit of our discussion of Fermi's golden rule and to discuss an example of that, and then to talk about broadband absorption, and then selection rules. So that's a lot of stuff. Selection rules for optical absorption. So these are related. Okay, so that's the plan for today. So let's sort of mention a little bit about last time. What we did was we talked about Fermi's golden rule. Fermi's golden rule. And Fermi's golden rule was this. We basically said that if we have a discrete state, with some energy, and if we're sitting in that discrete state and we perturb it with some harmonic potential at frequency omega, and suppose that this frequency omega is greater than that energy in the sense, and the reason I say that is because then this will lift us out into these continuum states. So this is equals 0, and this is E greater than 0, which is the continuum. And so if it takes us out to a continuum state, then out here, the state, we have a continuum of states. And so this is a very special case where we start in a single state and we have a transition to a continuum. All right, so this is important. It's a single state to a continuum. And you might think that that's very specific, and I guess it sort of is, but it turns out it's very common. It happens all the time that we're in a single state and then we have a transition to a continuum. It's very common, and so it's a big deal in physics. And so if this is the situation and we want to know, this energy right here will be EK plus H bar omega, then we want to know what's the probability of that transition. So then we found that R is equal to the probability to have a transition at time t divided by time t is equal to density of states at EK plus H bar omega times the matrix element linking the initial and final states, the perturbation, times a factor, which is pi over 2H bar. And so that's the rate. And this is equal to the number of transitions, the physical interpretation I mean, it's probability per time. I wrote it there, but the interpretation, the way we interpret it, is we think of it as the number of transitions per time. And so we think of we think of this idea of probability as transition. Because if the probability, for example, is, as an example, say 1/5, then that means that we have 1/5 of a transition. So I want you to sort of understand that, or think about it. And so here's like a way to think about it is consider, suppose we have, and this is where it becomes most important, suppose we have many atoms. And so we have a system here of n atoms. So here's an atom, here's an atom, there's another one here. Suppose we have a whole bunch of them, and they're all sitting there in their initial states, you know, that they're all identical. And now I shine light on all of these atoms at the same time with a laser. And then I can ask, what's the total number of transitions per time? And so suppose I know that for one transition, or for one atom, then suppose I know that the rate of transitions for that one atom is, you know, rho h prime squared pi over 2h bar from Fermi's golden rule. Then suppose this is known, then what is the total number of transitions per time for n atoms? Somebody tell me.
Should we just multiply by n?
That's exactly right. It's really simple. It's n times r. And so that's where quantum mechanics meets experiment. Because in an experiment, you have a gigantic, that could be Avogadro's number, right? You could have like, you know, a rabbit, and you want to know how much light does the rabbit, you know, or you might have a, you know, say a chunk of gold, and you want to know how much light does the chunk of gold absorb when I shine a certain radiation on it. And so you know how many atoms you have, and then you know how each gold atom responds, because that's where the quantum mechanics is there in calculating that number r. And so that's where quantum mechanics plays a role. But then if I have a macroscopic object, that's where the n, you see. So that's how it can be important. So let's do and let's do an example. So let's say that you're an electrical engineer and you want to design a burglar alarm. And so here's your burglar alarm. What you do is you take a chunk of silicon and you hook it up to a battery, and then you measure the current. And then you take the current that you measure and you send it to the computer. And then you say, the computer says, if I equals 0, then call the cops. It's an alarm, okay? So then that's your thing. That's your alarm. Now, what you do is you can do it like this, because normally the silicon will have no conductivity, but we do it like this. Check it out. We have a laser, and the laser is shooting a beam, and the silicon has a bunch of impurities, atoms. Now these impurity atoms are like little boxes, a bunch of little boxes. The impurity atoms. And here's the deal. The light, the current that you measure, I, is equal to the number of charge per number of time that is excited that can flow in the circuit. And so the amount of charge, to get charge, then you do this. This is what's happening. Each little atom has an electron sitting in the ground state. I'll call it phi naught. Let's call it, let's just call it the ground state, phi naught. And it's at some energy, epsilon. And so here's the light from the laser. And if the light from the laser causes this guy to come out, then that is measured as current. So every electron that is excited from an impurity atom in the silicon jumps out and is measured in your electrical circuit as current. Get it? If you don't get it, then ask a question, because this is a burglar alarm. Okay, so the idea is that if somebody steps in front of that laser, they block the light and the current stops because the electrons are no longer excited. Okay, so so this is like a real thing that people make, and so let's say that you're an electrical engineer, and you want to know what's the current. Because you need to know, if I have N, suppose that you can buy a chunk of silicon and you know how many impurities there are in the silicon because the manufacturer puts the impurities into it. That's called doping. And you want to know what that current is. So because if you buy a chunk of silicon with a certain number of dopants, and you know how strong your laser is, and so you want to know how much current you're going to get, because that's how you design the circuit. You need to know what current meter to stick into the circuit. Should you get a really sensitive one, or should you get, what is the sensitivity of the current meter? You got to know which current meter to stick into your circuit, which one to buy, how much it's going to cost. You're an engineer. You got to figure this stuff out. Okay, so you want to know what that current is. So you look at this thing and you think, okay, shit, how do I know what current is going to come out? Well, you realize, hey, I'm going to use some quantum mechanics. Let's calculate the current using quantum mechanics. So then I can know which current meter to buy so that I can make my burglar alarm and make a bunch of money. Because it all comes down to money, right? So you want to make a bunch of money. To make the money, you got to figure out what that current is going to be. So let's do it. Let's using quantum mechanics, because we know that for a given we know that the current is going to be equal to the number of impurities in the in the silicon times what? Somebody tell me.
Times R.
Exactly. And then there's one other factor to make the units right. N is a number, R is transitions per time. What do I need to make the units right to turn into a current?
The charge of an electron.
Exactly, which is minus E. That's exactly right. That's the current. That's the current that you will measure. And so, but the question.
I have a question about, so when we do this like N times R thing, we're implicitly assuming that all of the probabilistic processes are independent, right? Is that an approximation that we're making, or is it always independent?
It's pretty good, because, well, in this case, it's quite good because we're talking about impurities that are isolated in the silicon, and so one impurity is not really talking to another impurity. And so,
okay.
And another thing that happens too is in many systems, the transitions are infrequent. Like you have, you might have like little numbers, like they happen, every picosecond, but then there's time between them, and so it's usually like one, then it excites, and then there's a relaxation, then the next one happens, pink. And so, yeah, it's a pretty good approximation. They're often very independent, but not always.
But Yeah, wouldn't the particles like sometimes be entangled? Because they're identical.
Are they entangled? Because they're identical. No, they're not identical because the impurities are at different locations. So all that entanglement stuff isn't really applying here. Do you see what I'm saying? The atoms are at different locations. They're distinguishable. So yeah, the entanglement doesn't really play a role much here. I mean, you might be able to concoct something where the entanglement plays a role, but that's very artificial. That's not common. But what does happen, I will mention, is that sometimes charging plays a role. Like suppose that my silicon is really tiny, and then if I excite an electron out, then suppose that my silicon is so tiny that the charge of that charged impurity creates a Coulomb potential that the other impurities feel because they're so close to it, because there's so few. Then sometimes the charging effects play a role, but in macroscopic systems, the charging is irrelevant. Okay, so let's not get into those details. Okay, so all right, so let's so we have to find, so we must find R. And so how do we find R? Well, let's do this. We'll use Fermi's golden rule, right? Because we look and we go, oh my God, this is the situation. I have the electron in each impurity atom is sitting in the ground state, and it comes out into a dense set of final states, a continuum. And that's what I measure. That's what we measure is the current. So Fermi's golden rule tells us that R is equal to we have a constant pi over 2h bar, and then we have a matrix element that connects our initial state to the final state via the perturbation, and then we have a constant pi over 2h bar. And so we got to calculate this thing. So let's make an assumption. We have this situation. So just to make the calculation simpler, we're sitting here in the ground state, and the light is taking us out to some final state. I'll call that phi f. But let's assume, and this is not always the case, but just to make the math easier, let's assume that h bar omega is way bigger than epsilon. Okay, so we'll just assume a very small epsilon. And that is actually sometimes the case. That could happen. So let's not, it's not crazy. That assumption is not really crazy. For impurity levels, they can be very weakly, I'll call that a weakly bound impurity, and they happen.
Professor?
Yeah?
Should one of those pi over 2 h bars be the density of states?
Oh, yeah. I'm sorry. Oops. You're totally right. Okay, how's that? Does that look right?
Looks good.
Yeah, that's the final, that's the DOS of final states. But now we're just going to, we're going to make this assumption that it's just pi over 2h bar. We got to, and so now we got to calculate that matrix element times the density of states at h bar omega. Okay, so that's what we got to calculate. So let's calculate that sucker, because you're an engineer. You want to know the number because there's a real number. I mean, it's like 12, or 6, whatever. It's a real number. So let's figure it out, because that's what engineers do. They don't just play with equations. They need, in the end, to get a real number. And so let's figure it out. So here we have the situation, and we're coming out here to our final state, phi final. And so I know that I got to calculate this matrix element, and I know that it's going to be, I know that my matrix element is going to be, it's going to be due to the light. And so I'm going to have my phi final, and I'm going to have my phi initial, my starting point, and then I got to have my perturbation. And so what is that perturbation? Can someone tell me?
Is it a sinusoidal perturbation?
Well, remember when we derived Fermi's golden, it is, you know, it is a sinusoidal in time perturbation from the light. But remember when we did our Fermi's golden rule, we integrated out time. And remember, because we have the rate is probability per time. And so in our final answer, there's no time. The rate is a constant number. And so what is that perturbation that goes into this matrix element? I'll give you a hint. The perturbation is a constant part in time times the time part, the sinusoidal time part. The part that goes in the Fermi's golden rule is the time independent part. What is the time independent part of the perturbation?
Is it the magnitude of the electric field?
Yeah, that's totally right, it is. And so let's call that E naught. And so that's coming out of the laser. And we know that because the engineer is buying the laser and he knows the intensity of the laser. It's a number, so the engineer knows that. That's right, but there's more to it. What else is it?
The direction?
Was it E naught dot R?
Direction of what?
The propagation of the light?
No. Good guess though. But no, because the impurity atom is bathed by the electric field. It doesn't see the direction of the light, but it does see a direction. It's the direction of what?
Oh, yeah, it's the direction of the electric field.
Yes, otherwise known as the what? Say it again.
Polarization.
Exactly. It's the direction of the polarization. Good. And so let's suppose it's polarized in the x direction. So let's make this a one-dimensional problem. X. Could be z, but I chose x. So it's polarized in the x direction. So what comes after E naught?
X hat.
Exactly. X, the variable x or the operator x. That's right. What else am I missing? I'm missing one other thing.
Charge of an electron?
Exactly. Actually, it's negative charge of an electron. Since charge is negative E, it's a positive E. So that turns it into an energy. It's force times distance, right? Good. Okay, that's it. Perfect. Okay, so we got to calculate this thing and square it. So let's calculate that. And so then I need to know, so this, let's just assume that that's known. That's just the ground state of the atom, okay? Ground state. And so let's assume that's known because the engineer can look it up in a book, okay? It's for whatever atom impurity is, he knows the ground state of the impurity atom, he looks it up in a book. But what about this? What the heck is that? So that is going to be, here's the way to think about it. It's going to be the continuum states, continuum. And so these are the states, E versus K, they're momentum states. That's the continuum states. And you guys, this is the free particle continuum states. And you learned about these last semester, so it should not look too weird. Because what happens is the particle starts here and it gets jumped up by h bar omega. And so it gets jumped up to here. You see? That's h bar omega. And so this is the energy. And then this is the momentum. So then the particle then has, so then we know that the particle has E equals, so if I know the momentum K, what is the relationship between energy and K? Somebody tell me. If I know one, what's the other? If I know K, what's the energy? Somebody tell me.
So energy would be momentum squared over 2m.
Perfect. That's right. Free particle, it's kinetic energy. And what is P? Because we're talking, we like to use K, not P. What is P in terms of K?
H bar K.
Exactly. That's exactly right. And so that means that if the energy is equal to h bar omega is equal to h bar squared k squared over 2m, then that means that my k is equal to square root of 2m h bar omega over, did I get that right? Oh, I guess that's over h bar squared. Okay, so that's it. So that's k, whoops, over h bar. That's k, the square root. Okay, so that's k. Okay, you see I just inverted that equation. And so if that's my momentum, then what is my final state? Phi k is equal to what? What is the k? Because remember, my final state is an actual state. So what is that final state? We figured out that the light excites it up into this k momentum, h bar omega above. We figured that out, but what is the actual state? We're doing a calculation. What is the actual wave function of that state? Somebody tell me. And this is the state, this is the free particle state that you learned last semester. What is it?
Wouldn't it just be the plane wave? So it'd be e to the I k dot r.
Perfect. Let's just do it in one dimension to make the math easier. It's e to the I kx. But remember, we're engineers, and so we want a real number. And so when you're doing an actual calculation, it's often convenient to put everything into a big box, all right? To assume the actual length. So in this case, it'd be like the length of the circuit or the length of the chunk of silicon. So let's assume that the silicon has a length of, let's assume that our system has a length equals L. And so now what I can do is I can normalize it, 1 over square root of L. Okay, so I'm normalizing it because we want an actual number, okay? So that's my wave function, that's right. And so 1 over square root of L, the length of the system, times e to the I kx, where this is the k. Okay, so now everything is determined, like the engineer knows everything, okay? And so now the engineer can calculate the matrix element. H prime final initial is now going to be equal to an integral. And I can do, say, from, say, 0 to L. And I have my final state is 1 over square root of L e to the I kx, complex conjugate. I have my H prime, which is E naught x, and that E naught we know is the field coming out of the laser that the engineer knows. And then the initial state here is going to be phi naught of x, which is the ground state. And so that's an actual integral that you can solve, all right? So I want you to see that this is something you can really solve. So the engineer can plug that into Mathematica and solve and get an actual number, like 0.115, whatever. And so then, but the only thing that we're missing is what? So in order to calculate the rate, so now we got the matrix element, what are we missing? What are we missing? The engineer wants the number, huh?
Would it be the density of state?
Yeah. What is the density of states? Because we need a number. Okay, so what is the density of states? Well, that's the energy, that's the frequency of the laser. But what is the density of states of the final states? I mean, you know, it's we need a number. We need to actually calculate it. So we got to figure out density of states. Okay, so there's a formula for density of states, and I'm just going to derive it. I don't know. I think all of you have seen it derived before, but you might not remember it. It's the kind of thing that if you don't use it a lot, then you sort of quickly forget it, this concept of density of states. But it turns out that in the real world, density of states is very, very important. It is used all the time in physics. So if it doesn't make sense to you, now is the time for you to go study it and make it make sense to you. And if it doesn't, if you're having trouble, then you should come to office hours or something. I'm just saying that this is an important concept. So I will quickly derive density of states, but if this derivation doesn't make sense, then you should talk to Newton or me or something, or you're a friend. But this is an important concept. 3 exclamation points. Okay, so let's talk about it for briefly. So here it is. So here are my. So I'm going to kind of do a fast derivation of density of states. So here's my continuum states. You guys can tell I drink a lot of coffee this morning. I'm like really hyped, talking fast. So so here I am. I'm excited up to here. Some energy, which is h bar omega, the energy of the photon from the laser. So I'll just call it E, and that gives me, and I'm at some K. And so I want to know, what is my density of states? So here's the way to think about it. The states K are quantized, and that's states, K states are quantized. That's the easiest thing to remember. That's the starting point. And let's just see why that is. Because to make calculations easy, always put everything into a box. Box. And the box is of length L. And then we like to use periodic boundary conditions. Periodic boundary conditions. Meaning that this end of the box is connected to this end. So really, the box is a donut. Box equals donut. I don't even know how to spell donut. Okay, the box is a donut of length L. So this point is the same as this point. That means that my waves, my states have to be quantized, meaning that that's the ground state. Then the next one is 2 waves. And the next one is 3 wavelengths. In other words, L equals n times lambda for my states. And these are my K states. And so what that means then is that my wavelength of my momentum states is equal to L over n. But what that means then is that my K states, because that K is equal to 2 pi over lambda, so that means that K is equal to 2 pi over lambda, but lambda is equal to L over n, so K is equal to 2 pi n over L. Oh my God. So that means that K is quantized. K sub n equals 2 pi n over L. But then what then is the smallest increment of K? Delta K, the amount of momentum between my K states, delta K is what? Somebody tell me.
2 pi over L.
Exactly. Because if this is the K axis, then these are my K states. They're quantized. Where that is K1, K2, K3, and there's a distance between them of 2 pi over L. So K states are quantized when I'm living in a box. And so that's actually the easy part. So if you've never seen that before, then it's time for you to think about it. I'm assuming you have seen it before, though. This is used, for example, in the black body radiation derivation. So that means then that delta K equals 2 pi over L. So that means that the momentum per state is equal to 2 pi over L. And so that means that the number of states per momentum is equal to what? Somebody tell me.
L over 2 pi?
Yeah, you just invert it. Okay. Oh, shit, something happened here. Damn it. Oh, I put this into a weird mode. Sorry guys, I put this into some weird mode that I don't know how to get out of. Oh, I got out of it, yay. Okay, so that's right. So then that's the easy part, is to understand that momentum is quantized. And so what that means then is that if I go back to this original picture, I can see that my momentum states are quantized. You saw I'm just drawing it here. And so that means that if I take a little range of momentum, delta K, then I have a number of states here. I'll call it delta N states. But then if every one of these states in this little range of momentum, they all equal some range here. And so then, so this delta K in momentum space corresponds to a delta E in energy. You see that? There's a relationship. For every delta K, there's going to be a delta E. But that relationship is complicated. We don't know it. But the thing that we know is that if I know the number of states here, then what is the number of states here on the energy axis? What is the number of states? Somebody tell me.
The same.
Exactly, it has to be the same. And so that means that then if the number of states is the same, then that means that delta N on the energy axis is equal to delta N on the momentum axis, but delta N on the energy axis is equal to density of states times delta E. And so that has to equal density of states in K space times delta K. And so this is my favorite way to think of density of states, because this is density of states as a function of energy, and this is the density of states in K space, because density of states is equal to number of states per whatever, if it's energy, it's density of states per delta E or delta K. Well, actually, let me be more precise. I'll be more precise. DOS E is equal to number of states per delta E, and DOS K is equal to number of states per delta K. Okay, and so then we can then, from the simple equation, we then can see that the density of states is equal to, in energy, is equal to the density of states in K space times delta K divided by delta E. I just brought this this factor over. But this thing, delta K over delta E, is the same as using the calculus trick, dE dk, which is equal to dk dE, which is equal to dE dk inverse. All right, just using a little calculus trick that you guys have all seen this kind of thing before. So that's just a little calculus trick. And so then that's it. So then density of states is equal to density of states in K space times dE dk inverse. So we need to know these two things then. So we need to figure out what that is, and we got to figure out what that is. So let's do it. So what's density of states what's density of states for K space?
It would just be the L over 2 pi, right?
Exactly. And then how do we, exactly. And then to find dE, and then we know that E is equal to h bar squared K squared over 2m. So then to find the dE dk inverse, we just do dE, we just use a little calculus here, dE dk take the derivative of this thing, and it's going to be h bar squared k over m. But we know that k is equal to square root of 2me over h bar, right, from this equation. And so that means then that dE dk is equal to h bar squared over m times square root of 2me over h bar. And so then we can take this, so we have it, dE dk, and now we can plug it into here. So now we have it. So we have, so then we have, so then when you do all this, you're going to find that the density of states at h bar omega is going to be equal to L over 2 pi h bar square root of 2m over h bar omega. All right, and so that's what the engineer would do, and then you just plug it all in. And that's the end. So that's the Fermi golden rule example that I wanted to give you guys. Okay, so now let's move on to the next topic, which is broadband absorption. And this topic is it's sort of like a it's Fermi's golden rule, but it's done backwards. So it's sort of like, it's another Fermi's golden rule, but it's done sort of backwards. So it's a very cute problem, because what we did, what we did before was this. We said, what happens, what we did for Fermi's golden rule is we said, what happens if we have a particle that's in a discrete state and we excite it with a single harmonic excitation, h bar omega, one frequency, and then we had it go to a dense set of final states. Okay, this is what we did. And then we found the rate. And then we found that the rate is equal to, what was it, pi over 2h bar, pi over 2h bar matrix element squared times density of states, of the final states. Okay, so that's what we found. But now what we're going to do is something very related. What we're going to do is this. We're going to do this. Suppose instead we have a well-defined initial state and a well-defined final state, not a continuum. And we want to know the transition between two discrete states. But now check it out. This is what we're going to do. We're going to have a broadband frequency. And what does that mean? So this will be broadband. And what is a broadband frequency? So to get a single frequency turns out to be really hard. What do we use to make single frequency light? Can someone tell me?
Lasers.
Yes, lasers. Lasers were not invented until 1950. And so up until 1950, nobody could make a single frequency of light. I just want you to know that. So to make a single frequency of light turns out to be really hard. although you wouldn't know that, you know, because now we just take lasers for granted. But before before say 1955, nobody ever made a single frequency of light. Okay, so what people made up until the 50s was broadband light. How do you make broadband light?
Heat something up.
Yeah, you use a light bulb, exactly, or a candle. So a light bulb or a candle, otherwise known as, say, a flashlight, you know, it's like a light bulb, you know, a filament. So I'll call this a flashlight. That's right. If you have something hot, you know, a hot filament, it's radiating black body radiation. It's radiating a continuum of radiation. And if you guys know about black body radiation, then that is the continuum radiation. But if you don't know about black body radiation, then don't worry about it. But this is black body radiation. And so this is much more normal. You know, to have a continuum spectrum coming out of your flashlight is more normal. You know, that's like what's coming off of the sun on a light bulb and a candle. So this broadband spectrum is actually more normal, but it turns out that it's harder. The math is harder. It's harder to deal with the broadband radiation. That's why we always are talking about just one frequency. But in the real world, we have broadband light. So what we want to know is, we have broadband light, and so we want to know, if I have a flashlight shining on this atom, and the atom has a well-defined transition, what is the rate of transitions from the initial state to the final state? What is it? That's what we want to figure out. And what I want you to see is that these two problems are the same. It turns out it's the same problem. And so you can kind of see how, I mean, I haven't shown you mathematically yet that they're the same. You just sort of have to take my word, but I want you to look at it and intuitively kind of see, hey, those might be the same. Because in one case, in the first case, we're tickling the atom with a single frequency of light, but it's going to a broadband final state. Whereas in the second example, we're going from one discrete state to another, but we're tickling it with a broadband set of perturbations. So it turns out that the problems are both exactly the same. That's something that's really cute, and that's what I want to show you. So let's prove this. And so what we do then is how do we describe the broadband light? How do we describe the broadband light? It's not totally obvious, but it is actually simple. And so the way we describe it is what we say is that there's some, let's say that there's some energy density in the light. And so we'll say that the energy density in space, and this is stuff that you learn in E&M, so I'm gonna go fast on this. This is just, you know, standard electricity and magnetism. But the energy density in space is, I'll call that the total energy density of the light coming out of the flashlight. The total energy density in space, U sub T, is equal to a formula. Does anybody remember the formula? If I know the total, I can think of there being like a total electric field. I can add up, there's a bunch of frequencies, but I can add up all the frequencies and I can get a total electric field. And so if I know the total electric field, does anybody know what is the relationship between energy density and total electric field? Anybody know it?
Is it like half epsilon naught E total squared or something like that?
That's exactly right. That's exactly right. So that's the formula, and I know you've all seen it in some class that you took sometime. So there's that formula, but this is a little bit tricky because it's because this is adding up light at all frequencies, and so the way we do it is we say that we think of the total energy is equal to the integral of the energy density. where U of omega is equal to energy per frequency, hertz, energy per frequency. And so then what we do is we can say that we can define this U of omega, and we can just, so we can say that U of omega then is equal to 1/2 epsilon naught E of omega squared. So we can define this. We can define E of omega in this way. So E of omega is going to be equal to 2 U of omega over epsilon naught square root. Okay, so I'm defining my E of omega in terms of my U of omega, and I'm defining my U of omega in terms of my total energy. So my total energy is equal to an integral of this U of omega, where U of omega is, we call it the spectral density. And so this is, and so this electric field, so E of omega has units of electric field divided by, can you tell me what is in the denominator, the units? Can someone tell me the units? It has funny units. Can someone tell me the units?
Is it second?
Per hertz?
Yeah, like seconds in the denominator.
Yeah, but notice I did a square root. See, notice that U of omega has hertz in the denominator, but now I'm taking the square root of it. So what's in the denominator of E of omega?
Square root of hertz.
Yeah. And the only reason why I'm making a big deal about this is because we'll call, as an experimentalist out in the real world, often people will talk about energy per root hertz or power per root hertz. People often talk about per root hertz, and this is common out in the real world. And the first time you see it, it's very confusing. But the reason is because of this math. It's because of one thing is equal to the square of the other, and we take a square root, and you know, it's because of this relationship between energy and electric field. There's a square, and so that's why we get a root hertz there. But I don't want to belabor that point. I just wanted to mention it to you because any of you who are going to become experimentalists in the future, you will see this and you will be confused the first time you see it. Okay, so this is, so now, so we describe the light. So the light, broadband light is described by this, U of omega. And U of omega equals 1/2 epsilon naught E of omega squared. So I can define my E of omega squared is equal to 2 U of omega over epsilon naught. And I'm assuming that this is what's known. Okay? So when someone says I have broadband light, then what they're saying is that the U of omega is known, the energy spectral density. And so then the question is, so if I know U of omega, then what is the rate of transitions from my initial state to my final state? Well, here's the thing. It's like, if I have this is my initial state and this is my final state, then I know that if I'm shining some frequency omega on it, then I know what the rate of transition, I know what the probability of transition is. I know that the probability to be in the final state at time t, because this is, if I'm just considering one of the frequencies, then I know that. We figured that out. That's the harmonic perturbation. And so we know what that is. It's this. It's the matrix element that connects the initial and final state squared times this formula, sine squared, that we calculated in class. I take my final state, I take my initial, my initial state, that's the delta energy between them, and then I subtract h bar omega, and I have a T over 2h bar, and then here in the denominator, I have that energy difference thing, and it's squared. So that should look familiar. We did that in class last time. So that's the probability at time t that I have the trend that I've made the transition into the final state. But the trick is that there's many omegas, and so the total probability to get into that final state, total probability, I have to add up the probability that comes from every single one of those, because that's the probability for one particular omega. Put the omega there. And I have to add them all up. Do you see that? Because every frequency that's every frequency of light that is hitting that particle can induce it to do a transition. So if I want to know the total probability that does a transition, I just have to add up all of those perturbations. So it's like I'm adding up all of the perturbations. And so that's a key step. And so that's the trick, is that all the different frequencies of light in the broadband light, each of them is tickling the electron and making it want to do a transition, basically making its probability flow into the other state. So that's the key thing. And so then what we have to do is we then have to, so then what we have to do then is we see that the total probability to go into the final state at times t is going to be equal to the sum of this, but this is just this formula. So it's going to be the sum over all frequencies of this formula, which is simply this thing. I don't think I want to rewrite it, but it's, you know, it's this thing squared, and it's this sine squared of this stuff over this stuff squared. Okay, so it's going to be that formula. And so let's evaluate this sum. And so the first thing we'll do is find the matrix element. The matrix element. Okay, and so let's find that. And so so what we can see is that the matrix element is going to be two things, a sandwich. So what goes here on the left-hand side?
The final state.
Final state.
Exactly. What goes here on the right-hand side?
Initial state.
Exactly. And what goes in the middle?
Perturbation.
Exactly. And so that's going to be charge times what?
Electric field.
Right. But now the electric field is the electric field at a particular frequency, because I'm doing this at every frequency. So each of these is going to be a function of frequency. So it's the electric field at frequency omega dotted with what?
R.
Yeah, that's exactly right. So let's just, for simplicity, right now, what we can do is just, let's just assume that the electric field is parallel to Z. And so then this thing becomes the final state, E, E of omega Z, which is the same as I have E of omega, I have I'm going to write it like this. It's E of omega. I'm going to write it in a funny way. You can see it's phi f times E Z phi I. So this is H prime. That's the matrix element. But now I'm just going to do a funny thing. I'm going to put a little negative sign here and a little negative sign here, which I can do because they both add up multiplied to 1. But the reason why I do that is because what I can do now is I can define this as negative E of omega times this factor P F this new matrix element where P Fi is equal to this. And why did I do this? What is this? Why did I do that?
It's a dipole moment.
Exactly. That's exactly right. Because this is how people do it out in the real world. People recognize that this is the dipole moment, the electric dipole moment operator. And so this is the dipole moment matrix element. And so this is a very important realization, is that this matrix element, which causes the transition, the optical transition, this is the matrix element that controls whether or not an optical transition occurs. Because that's what we're talking about, right? We're talking about optical transitions. This is an atom. I have an initial state. I have a final state. I'm shooting with some light, and I want to know, does this transition occur? That's an optical transition. But the optical transition is controlled by the dipole moment matrix element. That's an important insight to see. Okay, so let's, where the dipole moment operator, I'll just define the dipole moment operator, P is equal to the sum. For any system, a dipole moment is defined as the sum of all the charges times the position of the charge. That's the definition of dipole moment. Electric dipole moment. Electric dipole moment. That's just something from E&M. Okay, that's the definition of an electric dipole moment. And if you have one charge, it's easy because it's just one charge times its position. Okay, so then what we can do is we see then that now we can evaluate this sum here. We will now evaluate that sum, because this was the dipole moment squared. And so we will evaluate that sum. Now we'll plug everything in because we see that the dipole moment H prime, well, we see the dipole moment up there. And so now I can write that sum, and I can see that the total probability at time t is going to equal the sum over all frequencies of E squared of omega Fi squared times sine squared EF minus EI minus H bar omega T over 2H bar divided by EF minus EI minus H bar omega squared. Okay, and so now what we can do is I have this I have this sum, but I want to turn it into an integral. And so what I can do is I can turn this into an integral because I use this relationship. I know that E squared of omega is equal to 2u of omega over epsilon naught. And so I will replace this with my 2u of omega over epsilon naught. And now I can turn this into an integral over frequency because that's a spectral density. So this is how I go from the sum to the integral. And now I can put this matrix element here. And now I have this sine squared stuff over the stuff squared. Okay, so I've turned the sum into an integral. And so now I just have to do that integral. But now to do the integral, I want you to see that now it's the same. We'll do the same math trick that we used for Fermi's golden rule. We're going to do the same math trick that we used before because I want you to recognize that this is the same integral as before. This is basically the same integral that we already solved for Fermi's golden rule. Because if you plot this thing, this function, sine squared of EF minus EI minus h bar omega, t over 2h bar, divided by this thing squared, if you plot it, then you see it's this famous function, sinc function. And so I have, if I plot it, I can see that at this point, I'll plot it so that this is EF minus EI, and this is h bar omega in this axis. And you can see that this thing gets really narrow. As time goes on, it gets more narrow, and this part goes up. So it gets narrower and taller as time goes on. And so it's a highly peaked function. Highly peaked at h bar omega is equal to EF minus EI. So it's highly peaked when the frequency is equal to that energy difference. And that should remind you of before. And so what that allows us to do then is it allows us to pull out, it allows us to pull stuff out, and we can see that the total probability at time t, now we can say is equal to 2 over epsilon naught. We can pull everything out of the integral. U of omega, I'll call that naught, where this is the integral from 0 to infinity, d omega of sine squared, all that stuff divided by all that stuff squared. Okay, where omega naught is equal to EF minus EI over h bar. So we're evaluating this stuff at that one frequency, but then I still have to do this integral. And so we did that integral before, and I'm not going to do the math, but there's a change of variables, same trick as before, and I'm not going to go through it. I'm not going to go through all the math, but when you go through all the math, then what you're going to find is that this probability is going to be equal to pi times time t over 2 epsilon naught h bar squared times p fi squared times u of omega naught, where omega naught is equal to EF minus I over H bar. And so this should look this should look really familiar to you. It's just like Fermi's golden rule. Just like Fermi's golden rule. Because here I have a matrix element squared, and here I have this continuum. Instead of a density of states, I have an energy density. Energy density of the light. And this is the matrix element. And so what we can do then is we can see that there's a rate of transitions. Rate R is equal to the probability divided by time, and I pull that time underneath, and then that is going to be pi over 2 epsilon naught h bar squared, the matrix element squared times the u at omega naught, the energy conserving u. So what that means then is that, so that means that the rate, so this is the rate of absorption of photons. Because you got to remember what we even have. I mean, we have an atom sitting in an initial state, jumping up to some final state. We have all these, we have this light hitting it, and this is my initial state and my final state, and so it's absorbing, it absorbs photons at omega naught equals EF minus EI over H bar, and the rate that it absorbs them is equal to this function. The rate is proportional to the dipole matrix element squared times the energy density of the light. That's the main result. So there's two important factors. There's the energy density of the light at the resonant frequency times the dipole matrix element. And so the dipole matrix element is really key. And so this explains color. Because look, if I have a leaf like on a tree, and that leaf is absorbing light, let's say that this is I final, and let's say that this EF minus EI over H bar corresponds to red light. Suppose that my leaf is absorbing red light, or let's say that the light is coming. I have a bunch of light from a light bulb, and that light bulb is the sun. Then it goes through. Then you see that the energy density that gets through is going to be the original energy density minus some amount of the energy density at the resonant frequency, because those photons are absorbed. They get absorbed, and so that means that the light that comes out, if I suck away the red light, I'm absorbing the red photons, then what does the light that comes out look like? If I suck away the red photons, then what am I left with? What is the color of the light? Can anyone guess?
It's like bluish.
Yeah, or green. it'll be like green. If you start sucking out one color, you're left with the other colors. You know, you have like red, green, blue. So I'm not like a big color expert, but but this is the idea. That's where color is coming from, because you're sucking out one component of the light, and then what's left is going to give you color. And there's different ways. I mean, I'm ignoring emission. It depends. You know, there's lots of complexities here, but I just want you to kind of get the basic gist of the idea. Okay, so that's all I want to say about absorption. But an important point about the absorption is that the absorption of light, the rate at which light is absorbed by an object, an atom, is proportional to the dipole matrix element times the energy density of the light at the resonant frequency. That's what we just derived. So this is the part that depends on the source, but this is where the quantum mechanics is. The quantum mechanics is living in there. And so let's take a close look. Let's consider that, let's take a closer look at this dipole matrix element, because this dipole matrix element is equal to the final state times the dipole operator, which for an electron is going to be minus E times R, the position of the electron, sandwiched with the initial state. So this is the dipole matrix element. And so something to consider is this concept of selection rule. The idea of a selection rule is that it turns out that from symmetry, what usually happens is that this is equal to 0 for atoms. It's usually, but sometimes it does not equal 0. So the question is, when does it not equal 0? That's an important question. So that's what a selection rule is. A selection rule is this question, because the idea is that I have a transition, and this is a very general concept. The transition is controlled by a matrix element squared. And the matrix element connects the final and initial states. And if the matrix element is 0, the transition does not happen. So if the matrix element equals 0, then there's no transition. So the question is, when does the matrix element not equal 0? Because then that's when you have transitions. And you have transitions. And the rule for when the matrix element does not equal 0 is called the selection rule. So there's this thing called the selection rule, which is just telling us when does the matrix element not equal 0, because that's when the transition can happen. So the selection rule tells us when does a transition happen. And so it turns out that for light hitting an atom, The selection rule is controlled by the dipole matrix element. The selection rule comes from this. I have a final state, I have my charge, I have R, and I have my initial state. So the question is, when does PFI not equal to 0? Because it turns out that when I have atomic states and I calculate this matrix element, it usually equals 0. And so the question is, when does it not equal 0? And so it turns out that after you do some math, you can show that if the final state is some state psi n prime, L prime, M prime, and if my initial state is psi n, L, M, then that's the final and that's the initial, then the dipole matrix element doesn't equal 0 if and only if delta L has to equal plus or minus 1 and delta M has to equal plus or minus 1 and 0, where delta L is equal to the final angular momentum minus the initial angular momentum, and delta M is equal to the final angular momentum minus the initial Z component of the angular momentum. And so that's the transition rule. So I didn't derive it, and so maybe we'll do that derivation next time. But I just wanted to mention this concept of selection rule. And so this is the part we skipped, was the math to show that. But maybe we'll do that next time. I'll have to decide. Okay, folks, that's it. I'll see you later.
Thank you.
Okay, bye-bye.